How's the volume? Okay. Waves from L as well, so it must be pretty good. Oh, the pocket of the belt wasn't trying to pocket that a bit.
You got that? Yeah.
No. Easy to launch the Falcon 9. Okay, so while Di's playing with the machine, this is a spiral galaxy called NGC 1300. It's about 61 light years from Earth, and we're able to look at it and see it and admire it and study it because of science and everybody's favourite telescope, the Hubble. You know, it's possible that in the far distant future, with an unimaginable kind of science, something we can't even dream of today, that we might be able to go there and look back at our own galaxy, which is also a spiral galaxy, and admire that from the distance. But that's dreaming. And I want to talk about science in the here and now, what we know and the way we know it, how science works. Now let's see if I can get this to go. Okay. So the scope of today's talk, I might as well close that down now.
Okay, so it's not even
Yeah. In fact, can I actually move it off there?
Of course.
If I may.
I think what you have to do is close all of that down.
Okay, that's all right. Okay, so the scope of today's talk, I'm going to start talking about what we mean by evidence, not just in science, and then we're going to move on to about how science works, what it does, and what it doesn't do. We're going to look at hypotheses, which are a key part of science, and we're going to design an experiment. And then we're going to look at the difference between laws and theories, and what makes them tick. And then after we've looked at a bunch of theories, we're going to actually use global warming as an example, and in particular the relationship between carbon dioxide and temperature. And then we're going to look at how climate modelling works, and what actually makes a model, what goes into a model, and what some of the problems with models are, and why prediction isn't such a precise thing as we'd like it to be. And then I want to talk a bit about investment in science, and why it's a really good idea. And before we kick off, I'd like to make one disclaimer. All the images you see on this presentation have come off the internet, and I thank very, very much all the people who put them up there and made them available for public use. And I hope no one's offended by these. And the other thing I want to say is, thanks to Di for starting a little bit early. I've got a huge amount of material to get through, and I'm really, really forgetful, and I'm easily distracted. So no questions until the end, otherwise I'll throw the pointer at you. But also, if you do need to duck off at 12, I'll try and finish by 12, but if you need to duck off at 12, that's fine, but you're going to miss the happy and optimistic bits right at the end. So moving on. You know, we've all seen enough television and enough movies about crimes and how crimes are solved to understand that, you know, there's a set procedure for this. And, you know, we just work through it all. And eventually, if there's enough evidence and it all lines up and points in the same direction, we get a conviction and we say that someone is guilty. In fact, you don't need to be very guilty to be convicted, but a little bit guilty, as long as it's beyond reasonable doubt. So in science, a similar thing happens. You need a lot of evidence before you decide that something is true in science, and you need to get that evidence from many different directions. You don't just do one little experiment and say, oh, I got a good result on this experiment, therefore it's true. Scientific truth doesn't work like that. It's always open to question. And that's why you sometimes read in the paper or hear on the radio, based on the available evidence, statement blah, 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 or XYZ, whatever it is probably true. And it's the kind of statement that drives politicians nuts. But there's a reason why something is probably true. And why do scientific truths change a lot? You might recognise these guys. I hope you do. If not, if you want to read a really great adventure story, Google those two names, Robin Warren and Barry Marshall. They're the guys who turned the treatment of stomach ulcers on its head. they found out that stomach ulcers are not caused by stress and spicy foods and excess stomach acid. Through a combination of careful observation and scepticism about the prevailing dogma, and some good experimental work, and a bit of luck, and some sheer raw courage, they managed to demonstrate that duodenal ulcers are caused by a bacterium that lives in the stomach. Fantastic. And they completely revolutionised across the whole globe the way that stomach ulcers are treated, and they won their Nobel Prize. Lovely people. So science starts with questions. Now, if it was just about asking questions, every child would be a scientist. But there's a little bit more to it than that. There's a lot of discipline, there's a lot of structure, a lot of organisation in science. It works like this. The first part is looking at the reality of the world, making observations, making measurements, and then asking questions. What might explain that? You know, what's going on? So we're all fairly familiar with that. And then science comes up with this thing called an hypothesis, and it's a big part of science, particularly when you work in statistics. And once you've got an hypothesis, you have to design an experiment to test it. Is that hypothesis is a real explanation or a wrong explanation? And most of the time, that hypothesis will just lead to more questions. If you're really lucky, it'll deliver you a scientific law, or it'll help to support an existing theory. But as I said, most of the time it just leads to more questions. A lot of science is circular. It goes round and round and round and round. More experiments, more questions, more experiments, more questions. That's how science works. What is an hypothesis? Okay, it's a reasonable guess based on observation, but also on some working knowledge of the subject. It's not a guess that's just thrown up in the sky. And from that guess, you come up with a potential answer to what you're seeing. And then the hard bit is designing experiments. That bit down the bottom here, let me just check that, that's the one. Whoa. Designing experiments is really hard work, but if you can't design an experiment to test your hypothesis, then that hypothesis sits in limbo. And sometimes the equipment or the technology is not available to test an hypothesis. And a question could be sitting out there for decades or even longer before the technology becomes available to run the test. And you can finally say, that hypothesis makes sense. Or you say, whoa, that was a real mistake. You know, we had that one wrong. Experimentation is the lifeblood of science. Now we're going to design an hypothesis. Anyone doesn't recognise Sean Connery and Dustin Hoffman? Okay. These couple of guys, they're about the same age. I think there's about 7 or 6 years between them. There's a big difference there. And it's very visible. Sean Connery has got even less hair than I do, whereas Dustin Hoffman has got a pretty full head of hair. But there's another difference between them. And this is a bit of a joke, folks, but don't get excited about it. Sean Connery is pretty tall. Dustin Hoffman is a little guy. So here's the hypothesis. Tall people go bald more than short people. Now, it might sound like a silly hypothesis, but think about it. If you were an advertising company wanting to advertise some hair restorer, you might want to know whether your target audience is going to identify with tall actors or short actors or basketball players or jockeys or whatever. And so you ask someone to run an experiment and test if this is true or not. So how would they do it? Well, I mean, you could look around this room and say, okay, hang on, there's a lot more women than men in this room. And women, on average, are shorter than men. So that would give you some funny data. It would introduce gender into height, and that's not going to work. And then what about age? What about health? And a scientist would ask all those sort of questions down the bottom. They're not complicated questions. You're all familiar with the concept. When you go to the supermarket and you want to buy an avocado, you sort of pick one out of the tray and you might tip it up and squeeze the stem in gently with your thumb. So yeah, it's ripe enough. But that is actually not a very scientific approach, because it doesn't tell you anything about the rest of the avocados in the tray, and it doesn't tell you anything at all about the ones in the back room that are still in the cooler. So this approach of just picking one up, which you've selected by eye even if you don't realise it, that's pretty good if you just want to put one on toast and mash it up, but it's not much help if you want to buy 200 for the restaurant for the weekend. So you need a more structured approach to it. And your hypothesis needs boundaries. So here's a possibility. Imagine that your hypothesis is that tall people living in Australia between this year and another 20 years off are going to go bald more than short people. What a logistic nightmare. I mean, apart from the fact that your data is going to go stale before 1938, the advertising company is going to say, no way, we're not paying for that. So forget that. It's got to be realistic. Is this more realistic? What about just going down to Main Beach with a clipboard and a tape measure next week and starting to measure people? Yeah, maybe, maybe not. Maybe not such a good idea, apart from the fact that you probably get punched. You're only sampling people who go to the beach. So your sample is biased against people like Miriam and I who don't go to the beach very often, and so you miss out on our data. And bias is really bad for good science, so you can't do that. Here's another possibility, that you could just go to the polling booth. Now, everybody goes through the polling booth, so that might work, but some people are pretty bad-tempered at the polling booth, and they might not want to be measured, and they might not want you looking at the top of their head and going, yes, no. But you get the idea. Sooner or later you can work out a way to gather some data, and then some lucky number cruncher is going to come up with a bunch of data organised a bit like this. And you can see here we've got men on one side and we've got women on the other. So we're separating those two categories. And then we're going to separate age groups. So we've got now 6 categories. And this is what science does. It breaks complicated questions up into small blocks of data, so that you can then start to consider them and compare them. And it does another thing. It gives you lots and lots of samples. So each of those blocks we have, maybe 10, maybe 50, maybe 100 pairs of data, hair and height, hair and height, hair and height. And we also have this miraculous thing called replication, or reps for short. And what replication does is it gets you independent sets of data. Now, you don't have to worry too much about that. There's no exam at the end. But what this does mean is you can run a statistical test on this called analysis of variance. And it will then tell you the probability of any one of those blocks being different to any of the other blocks. And that's a really very cool test. It's been around for a while. A guy called Fisher at Rothamsted University in the UK, he used it early last century to do fertiliser trials. And he really came up with this design. He perfected it. Fisher was a smart guy. And it's exactly the same design that we were looking at before, except instead of age groups, we've got vegetables down the left, and instead of men and women, we've got 2 different fertilisers, and instead of hair and height, we've got 2 different rates. But you can run analysis of variance on that, and this design works for everything. It's a really good design. Now, there are statistical tests available today to people like climate modellers, for instance, that are so far ahead of analysis of variance that you're comparing a pencil and paper to a supercomputer. They're just so much more powerful than this test. But the same principles still apply. Good experimental design, randomisation, careful sampling that's random, and replication, those things still really matter. So that principle runs right through science. Now, this is the bit that people struggle with. They say, okay, you do this experiment, it'll tell you if something's true or false, won't it? No, it won't. The best it'll do is tell you that something is wrong or probably not wrong. And this is where that element of doubt comes in. Why something is 95% probable, or it's a 97% confidence, or whatever. The mathematics of statistical analysis means that you cannot say that something is 100% correct. If you want that, then science is not your baby. But the good thing about that is it means that if new data turns up, you can revisit that question. You can come up with a new hypothesis, and you can run an experiment on that if you can design one, and bingo, you can see whether that new hypothesis is wrong or probably not wrong. And yes, we do tend to say it's true, because that's shorthand, and scientists are human as well. But when a scientist says that something is true about an hypothesis, he means it's probably not wrong. And that's an awkward little concept to get a hold of, but it's an important one to keep in your mind, because that's why scientists can change their conclusions. They can say, oh no, we were wrong. We found out more information, and this is now what we think is going on. It comes from that, from the idea that you can test an hypothesis and you can find out that it's probably not wrong, but you can't prove that it's right. There's always room for doubt. Now, the other thing about hypothesis and experimental design, and by the way, these are the twin foundations of experimental science. Without this, science doesn't move forward. An experiment has to be repeatable and it has to be replicable. What that means is that, let's say Miriam is the scientist, she does an experiment, she says, it's probably not wrong, I got this result, and she might have to do it 20 more times before she's comfortable that, yeah, I'm getting the same result every time, or a very similar result. I'm not getting any weird results that say, it's right half the time but not the other half, what's going on? It also has to be replicable. Other scientists have to be able to do it. So Di has to be able to run the same experiment in her home lab, or kitchen, or whatever. And that's why every scientific paper you read comes with a big section on materials and methods. And you don't have to worry about that too much today. But that's to help other scientists know what you did and see if they can get the same result. And if you haven't done a good job writing materials and methods, that other scientist is going to do a bad experiment, and you're going to get bad data, and that's bad science. So that part really matters. And that's why labs have certification certificates, and why equipment has to be calibrated, and all the boring stuff that science technicians have to do. So an hypothesis, just to sum that up, it gets tested to death before people finally decide it's probably not wrong. And of course, just as we leave this, some hypotheses are better not tested whatsoever. Righto. So after that sort of roundabout peculiar stuff, a scientific law looks pretty straightforward. A law is different to an hypothesis. A law is true for a start, and it's just some usually fairly narrow aspect of the natural world that is described by a short statement and a simple equation. The most famous example of this would be Einstein's equation of energy and mass equivalence, whereby if you convert a bunch of mass into energy, the energy that you obtain is equal to the mass you started with times the square of the speed of light. And we were discussing the speed of light this morning. It's 186,000 miles per second, or about 300,000 kilometres per second. So if you square that, it's an awful lot of zeros. And no equation has ever had more visible demonstration of its truth than E equals mc squared. It's a scarily true law. Scientific laws are the cornerstone of science. You know, without the truth of the laws that we use in science, that projector up there on the roof would be a paperweight. And I wouldn't be talking to you here because I'd still be walking from Karoi. They're all short and sweet and they're always true. Think about some of the common laws. I mean, we won't go into them in detail, but think about electricity. Ohm's law, that voltage is equal to the sum of current by resistance, V equals IR. That's one you probably learned in high school. Now imagine if that varied so that sometimes the voltage was equal to IR, but other times it was equal to I times 0.1 R, and other times it was equal to I times 1,000 R. You wouldn't dare touch a light switch, trust me. In fact, there wouldn't be light switches. V equals IR is why we have light switches. It's why electricity works. That law is never wrong. Gravitation. Imagine if your weight during the course of a day randomly fluctuated from 20 kilograms to 200 kilograms. You'd want to redesign the furniture, these plastic chairs, they're right out. Imagine if the laws of radioactive decay were variable, so that you couldn't go and have an X-ray because 50% of the time you'd get fried, and the other 50% of the time maybe it wouldn't work or maybe it would work. You know, those laws work. That's why X-rays are safe. A silly example, gas laws. If you've got 3 balloons and you blow the first one up, no problem, you've got a nice little balloon there. And you go to blow the second one up and you go, and it fills the room in one puff. Uh-oh, that's strange. So you pick up the third one and you blow until you're passing out. And so you put a compressor on it, nothing happens. It doesn't inflate. The gas laws aren't working. So good luck with the next kids party. It's just not going to happen. Gas laws are always reliable. You blow balloons up and they just stay blowing up until they go flat. So let's move on from laws, because laws are straightforward. They're always true, they always work. They're the foundations of everything we do. This is the source of one of the fundamental misunderstandings about science, the concept of theory. Now, For most of us, a theory is something, we chat to a neighbour about over a cup of tea in the morning. Go down the coffee shop and I'll tell you my theory about, the local football team, whatever. That's an idea, it's a conjecture, it's just a hunch. But in science, a theory is really powerful. A theory grows out of input from a lot of different sources, a lot of different information. And it explains broad swaths of the natural world, and it predicts the behaviour of broad swaths of the natural world. Those two, the only thing that the top theory and the bottom theory have got in common is the spelling. Theories work. They're accepted because they work. They're supported by lots and lots of observations, lots and lots of well-tested hypotheses have been repeatedly tested. And the other thing a theory has to do is you have to be able to make predictions using that theory, and the predictions come true. Like that big explosion I showed you a little while ago. This might seem strange. Science doesn't really care that a theory is complete or necessarily even accurate description of what's going on in the world, provided it works, provided you can use that theory to make predictions, to explain the natural world, then that theory is widely accepted and people will use it. If it works, it's accepted. And theories evolve and develop. As I said, it's got to be predictive. A theory must stand up to people running experiments to disprove it. People are always trying to disprove scientific theories. They design experiments and say, what if we do this? No, okay, it's still there. And a theory can evolve. If it's wrong, a theory gets thrown out. If you come up with enough evidence that the theory's not working, you toss it out. But sometimes theories just develop and evolve. And a good example would be this one here, Newton's law of planetary motion. Now Einstein came along and went, and rewrote this. Newton's equations weren't wrong. Newton's law wasn't wrong. It just wasn't a complete description. There was more to it. And Einstein came up with it. When you start to push up towards the speed of light, you need some additional equations. At low speed, Newton's laws work fine. And in fact, NASA went to the moon and back multiple times using Newton's equations. And one of the reasons is the arithmetic is a whole lot easier and you're a lot less likely to make a mistake and end up in the wrong place. When you get up to the speed of light, you've got to start using Einsteinian arithmetic, and that's not easy. But you can do this on the back of a scrap of paper. So here's some theories that fail, and there's some beauties here. And from the time of Aristotle until right up to Louis Pasteur, people used to think that lice and fleas and worms and maggots and even mice appeared just spontaneously. You throw a pile of straw in the corner and these things just arise out of it. It wasn't until Louis Pasteur turned up that, at least in the Western world, people went, there's actually more to it than that. And that whole idea of the spontaneous generation of life from inanimate matter was tossed on the scrap heap, because it didn't stand up to close inspection. It didn't stand up to experiment and careful measurement. Galen's theory of miasma, the idea that bad smells cause disease. No, bad smells don't cause disease. Bad smells come from the kinds of conditions where disease organisms can thrive, such as cholera. Vibrio cholera grows in stinky water and dirty ground. Galen probably killed a lot of people because he had them running around keeping the smells out instead of the germs out. The earth-centered, or alchemy. Alchemy is a beauty. When these guys weren't actually poisoning themselves, they were doing some pretty serious science. And Newton was an alchemist. Old Isaac himself, he was a very serious alchemist all his life. They really laid the foundation for modern chemistry. They got it wrong. Alchemy doesn't work. But a lot of their experimental work allowed people to do chemistry and help invent the modern world. So, well done, Isaac and the alchemists. The Earth-centered universe. Ptolemy's concept of these concentric shells with the Earth at the centre and then everything else arrayed around it. A phenomenal work of mathematical genius and conceptual genius, no doubt about it. But as soon as telescopes arrived, people went, no, that's rubbish. No, that's not how it works at all. And Copernicus came up with the idea that the sun is at the centre of the solar system, and the stars are way off there in the distance doing their own thing, and that's a much easier model to work with. and also all the evidence that's turned up since then suggests that's probably what's going on. But these guys were smart, so bravo to them. And then, of course, there's Velikovsky. You may remember him. He had some fame in the 60s and 70s with his theory of colliding planets and, you know, bits of moon flying off here and the origins of Venus. And the only people who pay any attention to Velikovsky now are makers of disaster movies and people who spend way too much time online looking at the conspiracy theories, because Velikovsky's theories have just been blown right out of the water. All the measured evidence says that Velikovsky was completely wrong, which is kind of unfortunate because it was a pretty image. Anyway, abusing scientific method. People do this, unfortunately. Scientists are only human, and some of them are in it for the game. And some just do it for other pressures. You know, they're asked to get a particular result. So you can manipulate the outcome of a scientific experiment by designing in such a way that an outcome is encouraged. Pharmaceutical companies are accused of doing this a lot. Whether they do or not, I don't know, because I don't actually have any evidence one way or the other. But they are accused of it, and it's easy to do with polls, online polls. It's easy to do with phone polls. It's easy to do with referenda. And that's why we still have a queen. Evidence shopping is another one. Evidence shopping is this thing of looking for evidence that supports one conclusion or one point of view and ignoring all contrary evidence. So politicians do this all the time, and that's why we still go down to the local pub and we can buy alcohol, but we can't go to the cafeteria and buy marijuana, even though there's plenty of evidence that marijuana is less socially damaging overall than alcohol, because evidence shopping persists in saying alcohol's okay and marijuana's dangerous. Whether it is or not, I don't know, but that's what the evidence shopping concept's about. And then there's inventing evidence, and this one is tricky. You may remember, must be 40 years ago now, 35 years ago, a couple of scientists said they achieved cold fusion. That they managed, at basically room temperature, working on the desktop in the laboratory, to fuse hydrogen together with other hydrogen and make helium. And that's the reaction that goes on the surface of the sun or within the sun. So normally it happens at very high temperature, but they said they'd figured out a way to do it using various catalysts that would do it at room temperature. And everyone went, wow, that's amazing. That's really going to pay off big time. But they hadn't drawn up the materials and methods very well, and everybody who tried to copy them, including themselves, failed. Because they'd just done a bad experiment. Their results weren't true. It was bad science. But then other people said, well, there's still money to be made out of this. I can get research grants and what have you. And so they started inventing evidence. And it's still going on today. If you go online and look at cold fusion, there are still people out there saying, I've achieved it, it's working, it's not working. Cold fusion at the moment seems to be rubbish, and logically it would be rubbish. But it doesn't stop people inventing the evidence in order to get some money out of the system. And of course, it's a really bad thing to publish this. So if you get caught, this is why journals like Nature, it's a big deal to publish a retraction. You know, when Nature comes out and says, we're withdrawing that article because there's some bad science in it, that matters, because the people who wrote that bad science, their career is basically down the toilet. And so 6 months of ridicule in the scientific journals is getting off very lightly. The standard operating procedure of science publications is to keep things low key. You don't see reputable science publications running around saying, we've got a cure for cancer. They don't do that. They say, we might have something that will help sometime in the future to work out the possibility of blah, blah, blah. And by the time you get to the end of it, you've fallen asleep, which is why newspapers say, we've got a cure for cancer. But the newspapers are talking rubbish, and the scientist is talking tentative because he's talking science. I love that comment from Carl Sagan that extraordinary claims require extraordinary evidence. But I love the picture even better. This is a picture of a gas and dust cloud called the Pillars of Creation. Again, it's a Hubble picture. It's about 7,000 light years away, so it's a fair old distance off. That's a dust cloud, an interstellar dust cloud, you know, the size of a galaxy. And in there, new stars are forming. But the old stars that have just formed, the light from those old stars, as they start to ignite and shine, their light is actually eroding that dust cloud away. So you're seeing the evolution of a galaxy right there in that picture. It's fabulous. And I'd like, because Carl Sagan was still alive when that picture was taken, I'd like to think he might have had it framed on his wall. He died a year later. Great picture. I thought I should put this in. You see a lot of stuff online about how to distinguish science from pseudoscience, and this just comes straight offline. It's okay to actually, where are we? It's okay to start with the conclusion and then work backwards to confirm, provided you then go through all these steps here. You can do your experiment, say, well, I've confirmed something, and then you get your peers and your other scientists to look at it. You look at all the evidence and arguments, whether it's for it or against it, and you make tentative claims. You don't make really bold claims. And if the evidence is against it, this pointer really doesn't work very well. If the evidence is against it, then you have to change your conclusions. You can't just stick with it. You can't be dogmatic and unyielding. I don't think anyone ever put this better than the late, great Richard Feynman. He was a wonderful scientist and a wonderful teacher. And he said, I'd rather have questions that you can't answer than answers that you can't question. You must be able to ask questions. Now, that doesn't mean that we should tolerate stupidity, but the freedom to ask questions that are well informed about a particular subject is the basis of good science, and it's also the basis of good democracy. We owe it to our fellow citizens to be well informed about science as much as possible and about how our country works as much as possible. And the greatest source of snake oil these days is probably the internet. And we could spend a lifetime debunking myths that you find on the internet. We're not going to do that, because you can do that for yourselves. What we're going to do is look at some theories that work. And we'll start with the special theory of relativity, because we've already had a bit of, this is the old E equals mc squared one. But it doesn't just blow things up. It lets your GPS work. Einstein's theory that he came up with over 100 years ago is one of the fundamental reasons that your GPS works. And then he came up with some other theories. The one about, instead of gravity being a straight up and down process, it's a curved process, so that you end up with people like Brian Cox on television smiling at you and trying to explain this and how it all works, and you go, I don't care because he's cute. Who cares? But curved space-time is a fabulous concept. And there seems to be more and more evidence coming up to prove that it's true. The general theory of relativity predicted a bunch of other things. Gravity waves. It was 100 years of waiting before detectors could be built that were sensitive enough to actually detect gravity waves. So there's Einstein back in 1915 saying, yeah, there will be gravity waves. And then 100 years later, at these two locations, Hanford and Livingston, said, oh yeah, we got them. And they've been measured many times since then. So gravity waves exist, which is kind of a backwards way of confirming that the general theory of relativity is a true theory, or a good theory, an acceptable theory, a theory that works. You notice how hard it is to avoid saying true? It's a natural thing that we do. Other theories, the Big Bang. Now, I really admire people who try and put the Big Bang theory into two-dimensional pictures like this, but when I look at it too hard, my head starts to hurt, and you're probably like me, so we're not going to do that. But the Big Bang theory works really well. For scientists, it explains a whole bunch of things that are worth knowing about, that are worth being able to discuss and predict. And the cosmic background radiation, the Big Bang theory predicted that. 1965, it was detected. Initially, the guys thought it was due to birdshit on the dish, but they got rid of that, and sure enough, it was the cosmic background radiation. This, again, this is the last picture from the Hubble, but I couldn't resist it. Under the best of conditions, standing on Earth, and with good eyesight, we can see 9 galaxies. We now believe that there are about 2 trillion galaxies out there. So the universe is going to be full of surprises. And a lot of this comes from the Big Bang theory. And when you can get a picture of it like that, you can say, that's not a bad theory, that really works. So other theories that work. Quantum theory, oh dear. This is the one that, you know, we just got used to Einstein and his funny curved space and all that stuff, and quantum theory turned up and it just ripped classical physics to shreds because it had effects coming after causes and it had locations that were here and there. And you know, if you've ever heard of Schrodinger's cat, you get a bit of an understanding of that. But it is really important for our technological world. All these things, you know, whether it's lasers or transistors or electron microscopes or the gravity wave detector, that relied on quantum theory. It underpins so many things that we just take for granted. And in the future, not too distant future, because an Australian scientist recently did some really good work on this, God bless her, we are probably going to have quantum computers. And the really cool thing about quantum computers is we might have genuine artificial intelligence. And then we can compare ourselves to something that's equally smart and see how smart we are. So Niels Bohr, who was one of the originators of quantum theory, he said that anyone who is not shocked by quantum theory doesn't understand it. And Richard Feynman, who used to teach quantum theory in his physics class, the first thing he used to tell his students every year was, don't worry if you can't understand quantum theory. Actually, nobody in the world understands quantum theory, including that dog. You don't have to. You just need to understand how to use it, how to make it work. Tectonics. You know, Wegener, for a long time, he was getting laughed at. People said this wasn't possibly true, but it sort of does work actually quite well. Plate tectonics is one of those theories that explains a lot of things that we like to know about. And what's more, we can track it by satellite measurement. We can now measure the rate of the speed at which those different tectonic plates move, roughly the speed that your fingernails grow at. But you can measure that from satellites. Germ theory. Now, we keep Louis the Fly under pretty tight control, and therefore we don't have to worry too much about the hazmat suits. We can save those for special occasions. Hygiene saves lives, and vaccines work. Evolution is another theory that cops a bit of stick occasionally. A lot of you will have seen that that sequence, you know, the evolution of horses, you know, from the little one up to the big one that we see today. And if you were a bit interested in that, you might have looked further and seen, you know, the evolution of the toes of the different kinds of horses as they moved up off their, you know, 4 fingers or 4 claws, and finally end up with the modern horse that's running around on his middle fingernail. That's evolution in operation. Evolution's not just about fossils, even if they're as pretty as this one. Absolutely gorgeous. There's now about 20 independent disciplines, not out there to produce evidence in favour of evolution. That's not their purpose. They're doing their own thing, but it all supports evolution. The evidence for evolution is astonishing, and it's just getting stronger and stronger over the last 220 years. Again, if you've ever paid any attention to evolutionary theory, you've probably seen a picture like this. And evolution explains this really well. It explains a lot of other things too, and it's particularly relevant now today that we've got all these DNA measuring tools and testing tools. The relationship between DNA testing and evolutionary theory is getting stronger every day. But if you want to see evolution in operation, if you want to actually see it happening, bacterial resistance to antibiotics is evolution at work. And because bacteria reproduce really, really quickly, like multiple generations within a day, some of them, that doesn't take long to happen. And so you can see it happening in real time. So to summarise, science works. We need to move on. An accepted hypothesis is probably not wrong. A law is always true, and an established theory explains a big chunk of reality. Now let's move on to the biggest theory of the moment. This is the theory that affects every man, woman and child alive today, whether they've heard of it or not, and whether they deny it or not. This theory affects everybody. It's been around a while. Arrhenius won a Nobel Prize, not for this particular work, but he was a Nobel Prize winning chemist from Sweden. And he was talking about greenhouse gases and global warming in the 19th century. It took a while for the evidence to turn up. The IPCC, which was formed from the World Meteorological Office and the UN Environment Programme in 1988, they release a report about every 6 years. And their first report, and by the way, they don't do science. They are scientists, they're experts in their field, but they don't do science. They look at all the published information on relevant subjects. They pull it all together and they pour through it, and they argue. They fight with each other all the time. They argue like crazy until they can come up with a consensus on what all that science means. So in 1990, they were saying we can't find evidence for human-induced global warming. In fact, they were really sceptical about it, so it's probably not humans that are doing this. Something else is going on. But every report since then, the probability that humans are the problem has gone up and up and up, like the blue level in the little body shapes, or from discernible, which means you can just detect it, through to very likely, extremely likely, from 67 to 90%, through to greater than 95%. When scientists start talking about greater than 95%, it's time to stop saying, oh, maybe something else is going on. That's really them saying, pay attention. This is very likely what is happening. It's probably not wrong. And a lot of work has gone on since then. You've probably all heard this. You know, when you're talking to someone who says it's only a theory and having that cup of tea and an argument, and they say, oh, the Earth's been poor and humanity survived been hot before and humanity survived quite well. Really? What does the peer-reviewed hard scientific evidence tell us about that? You know, just as you remember that the court needs a lot of evidence from different areas before they're going to convict Benny the burglar, well, science needs evidence from all over the place before they start talking about global warming. And they've got evidence from physics and chemistry. You know, these are really hard sciences. You do them in the laboratory under really controlled conditions. And that all says, yeah, the greenhouse gas effect, it's really going to work. It's going to make things hot. You can do all these different measurements. You can measure the greenhouse gases. You can measure the content of the greenhouse gases. And you can analyse CO2 in the atmosphere. And you can say, this amount of CO2 comes from burning coal and oil, and this amount of CO2 comes from chopping trees down, and this amount of CO2 comes from cows burping, because they all have their own individual isotopic signature. And all that evidence points to, yeah, we're putting most of the CO2 into the atmosphere these days. But what we're going to look at, oh, and by the way, you remember Verity talking about the progression of vintage dates? You know, wineries are buying land in Australia because they've been looking at their vintage dates for the last 100 years and saying it's getting earlier and earlier and earlier, and soon it's going to be happening in midsummer and there won't be any grapes there. Let's go somewhere further south where it's not that hot just yet. So they're all over this. They knew this before, probably before the IPCC actually picked it up. We're going to look at ice cores. And why? Ice cores are cool. Thank you. But ice cores are more than that. They're not just for keeping your drinks cold. They provide a lot of information. Ice cores are what you get when you drill down into the ice packs in Antarctica or Greenland or wherever, and you draw up a core like the one in that picture. And I'll show you some more in a moment. But each of those cores contains slices that represent a year. They represent the year's snowfall, and you can read them like tree rings. And there's a huge amount of information in each one of those. We won't go into them all. But the East Antarctica cores, if we're thinking about humans that have survived high temperatures before, they go back at least twice as long as humans have been alive on the planet. So we can look at what's happened during the whole history of humanity by looking at ice cores. So we're going to do that. Now, this is an ice core that's been polished up. So they take those ones and they put them in tubes in the Antarctic, and then they bring them back to Colorado in the US, and they put them on a little polisher, a little lathe affair, and they tidy them up like this, and you can see the rings. That black ring is a year when there was a volcano, and so there's a lot of volcanic ash and dust in the air, and so it shows up nicely. But up towards the left of that, you can get that working, yeah, up there, you can see what look like rings there as well. So that's roughly the thickness of the rings you're working with. And this is the US National Ice Laboratory. And let's hope Donald Trump doesn't think to turn the power off, otherwise the evidence is going to melt. The carbon dioxide and temperature data, and all the other data, and particularly carbon dioxide and temperature, because that's what we're looking at today, that supports the development and the validation of predictive models. And here's an example. People ask how models are made. They do this thing called hindcasting. And we all heard of forecasting. Well, this is hindcasting. It's looking backwards. And so the black line there, down the centre, that is real measured data. Now up here past, in the future, that's projected. But in the past, that's data that there are actually measurements for. And the coloured lines are different models that you can see up the top. And they're those agencies' attempts to model what has happened in the past. And the closer they can get their coloured line to the black line, the better their model. And so they'll model a chunk of that. So, okay, we've come up with some mathematical formulae, and we've got some software genius to put that into the computer for us, and oops, it's not working. So they do some adjustments and some changes and what have you, and they put it in until it's handling that piece quite well, and then they say, well, how well does it predict that? And how well does it predict this? And if it predicts well on both sides, then it's a good model. And if it predicts well into the future, well, we don't know, do we? Because that's the future. We haven't been there yet. But models try to look at the past under similar conditions so that we can predict what will happen in the future under similar conditions. And this is going to take a while. I did read recently, and I'll just get some water before I start on this because I'm going to need it. I apologise now because this graph is a little bit blurry, but it's the best example of this concept that I could find online. I did read recently that people struggle with two-axis graphs. I find that really hard to believe. I'd imagine that a two-axis graph is pretty straightforward, but just in case, the horizontal axis, that's this line across the bottom, is time, and we'll go into that in a little detail in a moment, and the vertical axis, that's this one here, is temperature relative to that green line. And that green line is temperature in the latter half of the 20th century. So about 40, 50 years ago, 30 years ago. So below that, the temperature is colder, and above that, the temperature is a lot hotter. In fact, that corner there, plus 14, whoa, where's it gone? Where's it gone? There we are. That corner up there where it's plus 14, on the top left-hand side, that's about twice as hot as the planet is today. That's about double today's temperature, because today's average temperature is roughly 14 degrees. So that's really hot. Now, the horizontal line, it's probably best if I come across and actually just do this by hand. It's divided up into 5 different blocks of time. And each of these little squiggles here represents a point where the scale changes. So from here on the right, from 0, that's today, back to here, time is measured in blocks of 5,000 years. But here we get to the squiggle, and we start measuring in blocks of 100,000 years. And then we get to that squiggle, and we start measuring in blocks of 1,000,000 years, and then 10 million years, and then 100 million years. And the reason we do that is if we put it all in the same scale as this, the other end will be somewhere down on Hastings Street, and we just can't use that. So think of it like a time microscope. You can crank the magnification up and look in close here on this scale, or you can wind the magnification right back and you can look broad brush over there at the left-hand side. And this scale goes back a long, long way. About 500 million years ago, the first complex life forms, the first multicellular life forms started to show up on Earth. And you can see how hot it was. It was really hot. And then it got cold for about 100 million years. You may have seen that snowball Earth image on the internet occasionally. But yeah, it was really cold. But then it got warm again, and we had dinosaurs, and they rocked the joint for about 160 million years. If you put the life of dinosaurs there, it's just everything. If you put it all at this scale. Anything else that's happened just doesn't matter. Dinosaurs, they ruled for a really long time. So then we change the scale, we get out of that 100 million year era, and we get into the 10 million year era, and we've got Gondwana starting to break up. Gondwana is still breaking up. India is still pushing up against the Eurasian plate and pushing the Himalayas up. But the big breakup has started to occur back then. And then about 7 or 8 million years ago, the first tiny little ancestors of the primates, that's, you know, the ape-like creatures that we are, it first showed up hiding under a leaf, you know, trying not to get eaten by all the other stuff that was hanging around. And then about 5 million years ago, the first hominids. Now these weren't humans. Elle's been reading Harari's book, so she knows all about this. But these aren't humans. They're sort of a bit like humans. They're close enough to humans to be clearly related, but they're just called hominids. And this was the very early ones. And then about 2 million years ago, one of the hominid groups, and this is one of the later ones, they started making stone tools. So this is getting pretty sophisticated. They did a lot of other stuff as well, but we'll just put stone tools in there. And nothing much changed for nearly 2 million years. All these different hominid groups, all different kinds of proto-humans, and then humans turned up, and they kept on making stone tools too. Seemed like a pretty good idea. It's working for everybody else. Why change? And then about 12,000 years ago, because now we're into this modern era, about 12,000 years ago, humans, Homo sapiens, started making pottery. And they'd only just got this figured out, you know, pottery's good stuff, we can keep things in it. And then someone got the bright idea of doing agriculture, and before you knew it, they were making pyramids and building cities. And, you know, the world changed. The world changed dramatically, and humans changed, our whole behaviour changed. Our ice cores now go back about 1 million years. That's the Russian ones from Vostok. We're only going to look at the American ones, which go back about 800,000 years. And in fact, to start with, we'll only look here, the ones that go back about 400,000. And that's just because the information available fits in that 400,000 year period. And once we've looked at that 400,000 years, we're then going to look more closely at this period since the end of the last ice age until modern times. And then we're going to look at modern times. So that'll be the prediction and speculation time. So there's a lot going on that graph, and I appreciate it probably does take a little bit of following. We'll glimpse it again later on. But basically, what you can draw from that is when it's been really hot in the past, there weren't any humans around. And we'll look up here, and we'll look at what those hot spells meant, just a couple there, what they really meant for humans at the time. So this is that 400,000 years. Now this is a very famous graph, and you might have seen versions of this already. Again, it's a horizontal scale on the bottom, running across the bottom, so this is the present here, going back to 400,000 years. And on the left-hand side, that blue line is carbon dioxide, that's the blue scale, and on the right-hand side, that's the temperature scale. And those two things are going up and down in lockstep. When people saw this, they got really excited and said, yes, carbon dioxide and temperature, they are so closely related. And by the way, that's how long humans have been around on the scale, at least 300,000 years. So, you know, they've been through a couple of warm patches, but not terribly hot. If you look at the temperature scale on the right, yeah, 2 to 3 degrees warmer. We're not talking 14. Now, a thing about this is that a process called orbital mechanics explains that sawtooth stuff, the periodicity, the up and down on a regular basis. Every 100,000 or so years, you know, you've got a hot time, and then you've got an ice age, and then you've got hot, and then you've got an ice age. It happens at about 100,000 year intervals. Orbital mechanics explains that. It doesn't explain this. This one, climate deniers use this for a long time and said, yeah, okay, orbital mechanics explains it all, and carbon dioxide is not related because carbon dioxide follows after the temperature rise, so therefore you're wrong. Now, what's going on? That's a really important question to ask. It's a good question to ask, and not just because you're a climate denier. Why does temperature start to rise before CO2? We'll explain that, but first we're going to look at what are called the Milankovitch cycles, because orbital mechanics are interesting. If you want to know more about this, Google's your very good friend, and it's very easy to find, there's a lot there, but there are 3 things about it. First one is eccentricity, the shape of the Earth's orbit. It varies from very, very circular to a little bit of an oval, to an ellipse. And when it's circular, the sun is close to the Earth all the time, and so the Earth gets a little bit more solar radiation. The tilt This is the the tilt of the Earth, because the north-south axis doesn't run vertically through the Earth. The Earth is a little bit tilted. So sometimes that tilt is extreme and the Earth's getting sun on the top of the head, and sometimes the tilt is straight up and so my nose gets burnt. This doesn't really change the amount of heat that's arriving on Earth, but it does change where it falls, so it's pretty important. And then there's this one, which is precession, because like a spinning top, it moves around. And when it moves around, that changes where the maximum amount of solar radiation falls at a particular period of the Earth. So these are all on different time frames, by the way. You can see that we talk 100,000 years and 41 and about 30. So when they all line up, you get a bit of extra heat. But it turns out that with the best will in the world, there's not enough extra heat to melt all the ice. You can't end an ice age just by having all those different parts of the Milankovitch cycle line up. You can start the warming, but you can't complete it. And other factors, especially CO2, it's the main one, they're really important. So we've been looking at this period here, that 400,000 years. Now we're going to look more closely at why the temperatures start to rise before the carbon dioxide. We're going to look at this period here, since the last ice age, and the reason is we've got some really good data for that. And it'll tell us a lot about what's going on. That's this period here, different scale, since the last ice age, okay? The LGM, that little thing you can see there, last glacial minimum, it's just a different scale. So you can see it crammed in there or spread out. So a very smart guy called Jeremy Shakin, who works, I think, at Boston College, a really interesting scientist, not he's a young fellow. He asked that question of himself, why on earth, what's going on? Why does the heat start going up before the CO2? Is the Antarctic ice core measurements a really good representation? Does it really reflect global temperatures? And in the last few years, a lot more data has come available. And it's from various different areas, and some really cunning science has gone into making this data work. Some of the isotope work, I just look at it and think, okay, that's clever, and move right along. It used to be that, in that sawtooth graph you saw, it came from those 4 locations in the Antarctic. Now, there are 20 times more data points available for calculating what's happening with carbon dioxide and temperature around the world. And they come from all over the world, so you've got a much, much better picture. Scientists love data. More data gives you a better picture. We're going to come back to this, so don't spend a lot of time looking at it. But the orbital trigger is down here. This is when all the Milankovitch cycles line up and say, okay, we're going to start putting as much heat as we can into the Earth. It's not very much, but it might be enough to melt some ice. And then you can see the yellow dots represent carbon dioxide levels in the atmosphere, and the blue line represents global average temperatures, and the red line represents Antarctic temperatures. And now they're spread out a bit. So Shakin didn't just come up with that chart, he came up with a mechanism to explain what was being shown there, to how this was actually operating. And he used real measurements. He said, okay, here's an hypothesis. I think this might be happening, and he went out and he took samples from all those other data points that we were looking at, the globe of the Earth, and said, yeah, that supports it. So it's a pretty good hypothesis. 19,000 years ago, it's very time specific, I love that. He said that orbital trigger started melting ice over Greenland and a bit of North America and a bit of Europe. And for about 1,000 years that ice kept melting. Not a whole lot, because there just wasn't enough energy, but enough ice melted so there was a big flood of water into the North Atlantic. And that disrupted the global ocean circulation currents, this thing called the thermohalone circulation. And this one's pretty cool. What it does is it takes heat from the Pacific and it flows across here, across the Indian Ocean, and up through the South Atlantic, up to the North Atlantic, and it loses all that heat. And that's why people can live up here, by the way, because this current is bringing heat up. And then the water cools and it sinks and it flows all the way back at depth. So the warm water's flowing on the surface, the cold water's flowing underneath, and about 1,000 years later it arrives back here. And this is still going on. This is a major event in the world today. So red flows on the surface, and it's nice and warm. It takes heat from the Pacific and from the south, and it moves it to the north. And of course, we'll just actually pass that, when the ice starts to melt here, in this area, it can't flow out through the Bering Straits because they're not big enough. It's like a cork. And it was probably frozen over anyway because all the heat was falling on this part and the ice was pretty well around there. So all that fresh water for 1,000 years just flowed into the North Atlantic. And that's what stopped that circulation. And Shaken was able to find sediment data in ocean beds and lake beds to support this hypothesis, which I think is extraordinary. And the dominoes just kept on falling. You stop that current, and suddenly the southern oceans start to warm up. Instead of losing that heat up the top of the Atlantic every 1,000 years, they stopped. So they're just getting warmer and warmer and warmer every year. And carbon dioxide starts to come out of the water because carbon dioxide isn't very soluble in warm water. The more you heat it, the more carbon dioxide comes out. And so the levels of carbon dioxide in the atmosphere started to go up. And there's a lot of water in the southern hemisphere. It's mostly water. So as more and more ice melted and more water warmed up, and as it started to be exposed by ice sheets retreating, that's a lot of carbon dioxide coming out. And so it's the final domino. And again, it was only about 500 years. After that current stopped, it took about 500 years before there was enough carbon dioxide in the atmosphere for the feedback loop to establish so that carbon dioxide is there, greenhouse gases, greenhouse effect, temperature starts to rise. Oceans get warmer, more carbon dioxide comes out. Temperature keeps rising. That feedback loop established. And what Shaken found was that about 93% of the warming actually took place after the rise of carbon dioxide. So we had the orbital trigger, and then we had this little period down here, this little circle, and in here for about 7% of the warming cycle, heating was ahead of carbon dioxide. But then very, very quickly, that feedback loop established, and you can see the carbon dioxide is going up and up and up, and the global temperature is lagging behind it. Now in the middle there's a bit of a flip. That's probably a volcanic period when there's a lot of crud going into the atmosphere, and that just slows down the amount of heat reaching the Earth. But the atmosphere cleared, and the temperatures kept going up and up until about there, where humans got the idea that agriculture was a good thing to do. Now it begs the question, why did it stop? You know, this feedback loop, what stopped it? And that's a really good question. And the answer is we don't know. I love this kind of, the full explanation for this observation is still an active area of research. How many times have we heard that? Or something like it. But there are some really good hypotheses. When people come up with that top sentence, what they generally mean is, look, we've got a lot of ideas, we've got a lot of data to pull through, we need to run a lot of experiments, and we'll get back to you. There's many things probably happening in combination. One of them is this. When it says increased volcanic activity, I found this kind of interesting. We don't tend to think of the difference between the continental crust and the ocean crust is, that they float around. But they actually float on the mantle rocks. And when you move water out of the ocean and you put it on the land, big masses of water, to make big masses of ice, that ice presses the continental crust down. And at the same time, because you've taken a lot of the weight of the water off the ocean crust, it rises up. And so, bang, they sort of rub against each other. It's like putting a cork in a bottle. And then once your ice age stops, and you melt all that, the continental crust actually rises up, and this can be measured. So there's quite good data supporting this. And the oceanic crust, because it's got so much more water on it, it sinks a bit. And so instead of that cork, you open it up. And that's a route that volcanoes can start to operate. And there's actually quite good data showing an increase in volcanic ash during interglacials. So maybe this theory will be accepted one day. Maybe it'll be fine-tuned, maybe it'll be adjusted. But I thought it's a kind of nice little theory to look at. And now we move on to prediction. And in 10 minutes, we're going to have to race through prediction. I said earlier that you can accurately predict the future under similar conditions, so that begs the question, how similar are CO2 and temperature going to be in the future? And the answer with carbon dioxide is not similar at all, unfortunately. That horizontal line, okay, the scale again, this is the present day, this is back 800,000 years, and that's, I think, yep, that's, okay, so Homo sapiens has been around for about 300,000 years, so that's 2.5 times longer than people have been here. That line there, 300 parts per million. Carbon dioxide hasn't been above 300 parts per million until quite recently. We're actually now at 400 parts per million, and it's rising faster than it ever has, and it looks like going quite a lot higher. The lower emissions, this is burning less coal, less oil, chopping down less trees and teaching the cows some manners. That's the lower emission scenario. That one's going to put us at about almost double what we've got today, what we used to have. And up here, this is quite high. If we just continue burning coal, etc., we're going to have a lot of carbon dioxide. And it's really hard to predict what that's going to do because it's rising faster than it ever has in the past. It's hard to determine what the sensitivity of temperature is going to be to carbon dioxide when it's just racing away. When you look at temperature, again, the answer is not similar at all. We just don't know. It's never risen this fast in modern history. Again, time scale, 0, back 12,000 years, pottery, agriculture, pyramids. This is the late 20th century temperature, and the scale on the left is minus 0.50, 0.51. So it's not a particularly long scale. That's why there's a bit of a bow in that. But you can see that it used to be hotter, and then it got cooler, and now in the industrial era, we're as hot as we've ever been since agriculture began. And indeed, since we first began inventing pottery and burning things. When we say it's rising faster than any time in human history, this is where we start to get into the scary stuff. It's 10 times faster than any time since the last ice age. And new records just keep flooding in. For the first 80 years of the 20th century, a new temperature record was set every 13.5 years. Global warming had begun, but we weren't really sure what was causing it. In the last 20 years, those records are being set every 3 years. And in our 21st century, we're setting records just about every year. As Verity said just the start of this year, 2017 was the first record temperature year in the absence of an El Nino ever. The next El Nino we get could really change some rules. So this is the IPCC. This is the guys who look at all the data in the world, and they said this in 2014. You can't argue with global warming anymore. Sorry guys, it's happening. That greenhouse gases, and that includes all the other greenhouse gases, they're the highest they've been for 800,000 years. You saw that chart. That's the same information they work with. And they said, we're starting to push 100%, which is really scary, that human influence is the dominant cause of global warming. That we're responsible. When scientists and groups like IPCC start saying close to 100%, take them seriously. So modelling the future, how do you go about it? What's going to happen? Well, it's a difficult challenge. That's another one of those science speak things that says, it's not easy. Just because it's not easy doesn't mean we shouldn't do it. There are data that can help us, and we can come up with probabilities and a range of likely scenarios. So again, that same scale, conditions are not similar, so how do we do it? We say at the lowest sensitivity, when carbon dioxide isn't going to be a major influence, maybe we're going to be 2 degrees warmer than we are today. At high sensitivity, maybe we're going to be 6 degrees warmer. That's the scale on the left. And this particular model said, most likely warming somewhere in the middle. Who knows? That's a bit of a cop-out. The IPCC said this, unless we do something to slow down global warming, we're probably going to hit 3.7 to 4.8. Now this was written before the Paris deal, so that number might be a little bit different today, but the range was 2.5 to 7.8. And with America pulling out of the Paris deal, maybe this one still holds. So it's going to get warmer. Now, the last time it was almost 4 degrees hotter was 120,000 years ago. And guess what? There are hardly any of us. There are as many people living in Queensland today as there were living on the planet when agriculture first developed. That's the population of the entire world 10,000 years ago was the same as the population of Queensland today. That doesn't give us a lot of wiggle room. It does give us a lot of resources to do something about it. I must admit that if 6 or 7 billion or 8 billion people can put their shoulders to the wheel, we could really do something about this. But we have to agree on that in the first place. This is again what the IPCC, and it's scary. If we don't do something, we're in trouble. And about now, if that's what the focus of this talk was, I'd start showing you slides like these and trying to get you to hide under the furniture. But I'm not. This is Richard Alley. Lovely man, lovely scientist, respected by all climate scientists around the world. Even the Republican Party respects Richard Alley. And they've invited him to talk to Congress. He's put out a really good paper called 4.6 billion years of Earth's climate history and the role of CO2. He regards CO2 as the control button, the control dial for Earth's temperature. And if you've got 25 minutes to spare, Google Richard Alley, billion, and CO2. It'll be the best 25 minutes of learning you'll ever spend. The guy's great. But he said something which I found quite quite challenging, that the past climate's interesting, but it's not a lot of help with the future. And he's right, and I thought about it. What is a help with the future is investment in science. And so really, for the next 5 minutes, and I'm sorry we're starting to run up to 12 o'clock, but we're getting close to the end, I want to talk about investment in science and why we should fund it. There are lots of valid reasons, many of which our government doesn't get, but you think about what CSIRO has meant to Australia, what DSIR has meant in New Zealand. You know, these are great science organisations, and you think about the things that have come out of science, the technologies and the commercial applications, and the possibilities for saving the planet. We're going to look at some of this. These are some technologies built on science. Now, the guy who discovered the photovoltaic effect was 140 years ago, something like that. He wasn't thinking about solar panels. He was just mucking around in the lab and going, oh, that's interesting. And yet now, Queensland is doubling the amount of solar electricity this year. Fabulous. That's a technology that just came straight out of pure science. The World Wide Web really came out of a bunch of nuclear physicists wanting to swap data around the world without having to wait for it. Dustin Hoffman's father-in-law in The Graduate said, get into plastics lab. He wasn't thinking about 3D printers. And yet now we have 3D printers that rely on plastics and they rely on computer files. And you've been looking at those fabulous pictures from the Hubble telescope. They come from science. That's what they're about. Commercial applications? Wow. I had a friend when I was living in Dunedin in New Zealand back in the early 70s, and he was studying lasers at university doing his master's degree. He had no idea what they were for. He was just playing with lasers. Here you go. And I'd like to talk to him, I think he's still around somewhere, and just find out what he thinks of the applications we now have for lasers. They're amazing. The lab techs who first came up with the formulae, the composition of steroid hormones, they were not thinking about having good times. But never mind, oral contraceptives. PET scans that, Pamsy, I don't know if the Noosa Hospital's got a PET scanner or not, but it's the same technology that the Large Hadron Collider uses for detecting Higgs particles. Exactly the same, it's just a bit different scale, but that's how it works. DNA polymerase primers, these are the little things that allow you to cut DNA up and then multiply it and make more and more and run all the cool tests that allow you to do DNA sequencing and they also support Hollywood and CSI and things like that. But no one who was looking at polymerase primers could envisage the way we use them today. And then the science for saving the planet. This isn't just a good idea. If we could retire coal and replace it with renewable energy, we would get rid of about definitely the single biggest chunk of greenhouse gases that comes from any human activity. Coal is the number one, burning it for electricity. And that's a really good thing to be pressuring your politicians about. Fusion energy, this is hot fusion. I'm not talking about cold desktop fusion. I'm talking about fusion reactors that have been soaking up money and science and effort for 50 years at least. Still not there, getting closer every year, bit by bit by bit. Imagine if you had endless energy with no worry about nuclear waste and no worry about people stealing stuff to make weapons, and the fuel was just water. Fusion energy is pretty exciting. And if you had that, all the deserts of the world could suddenly start producing food, and all the pipe dreams would be wonderful stuff. Or just hydrogen fuel, don't worry about a fusion reactor, just burn hydrogen. That, the exhaust is water, great thing. And if battery technology doesn't develop well enough, then transport, heavy transport, shipping and long distance transport, hydrogen fuel could be the way that goes. Electric cars. Now Bloomberg, the really radical left-wing Bloomberg magazine, they reckon that by 2022, electric cars will be cheaper than internal combustion engines. That's something to think about. At the moment they're subsidised, but by 2022 they should be able to stand on their own. CSRO is doing really good things with water filtration. If you want to save the planet and stop people having to move around to look for water, helping them to clean up dirty water where they live is a really good technology. Recyclable, edible plastics, and people do that all the time. Lab-grown meats. Hey, I might actually be willing to give up lamb chops if it's going to save the planet. This one, artificial photosynthesis. Now, the carbon capture and storage thing that was around for a while, and people kept saying, oh, we'll suck the carbon dioxide out of the stack over the coal-fired electricity plant, and we'll condense it and we'll pump it into the ground. That seems to be dead in the water. No one believes that can ever happen. But Bill Gates and his mates, they've got a prototype of this working in Western Canada, I should say. And their vision with this is to produce liquid fuel, sucking carbon dioxide out of the air through artificial photosynthesis, do an abracadabra to it, and getting petrol out of the other end, or something like petrol. If that works, then maybe internal combustion engines get a second life, because that's a carbon neutral technology. There's lots of things going okay. It's okay to be optimistic about the future. And that's the reason that I didn't want to scare you to death and show you lots of horrible pictures today. We do have to do something about the future, and we've got to keep some pressure on our politicians, and we've got to let them understand, help them to understand that we support good science action, and we support good science practice, and we support sensible policy across the board. Here's another person, Joanne Chory, great woman. She spent the last 30 years working on botany and genetics, and just won a whole bunch of awards for it. She works at the Salk Institute in San Diego, and now she's got her whole team working on improving the way that crop plants turn carbon dioxide into suberin. Now, you all know what suberin is. Anytime you open well, not now when you unscrew the cap, but if you pull a cork out of a wine bottle, that cork is mostly made up of suberin. And if you've thrown a cork into a compost bin, you know that it doesn't go away. Every time you turn over the compost, that cork just laughs at you. Suberin lasts a long, long time in the ground, and that's really important, because at the moment, when you use crops for sequestering carbon, and you get a seasonal blip, maybe you get a hot year or something, and that carbon just goes straight back into the atmosphere. Crops are not very effective at sequestering carbon. If you can help a crop to sequester a lot more carbon than it does in the form of suberin that lasts for a long, long time in the ground, then you can really do some good. Imagine putting that in the hands of Farmers for Climate Action. They might get excited about that. This was Chory's back of the envelope calculation. 5% of the cropland of the world, we could get 50% of the human released carbon dioxide out of the atmosphere. Good luck to her, I say. She makes me feel really optimistic. A couple of things. Science is not technology. To have technology, you need science, and you need engineering in the broadest sense, and you need innovation. Nor is science commercial outcomes. For commercial outcomes, you've got to have technology and entrepreneurial effort, government support, whatever. But what science is, it's the most effective system that humans have ever developed to understand and explore physical reality. It works because it embraces doubt, it lets you ask questions. It avoids assumptions as much as possible. It's a disciplined process of not leaping to conclusions. It tests the answers and it trusts the evidence. And we can use the findings of science as fertiliser to grow a really good future, or we can just bury it and hope it all goes away. It's up to us.
Thank you. I don't think they'll ever stop clapping because that was fantastic, wasn't it? Yes. Truly, truly astonishing. We can only imagine how many hours of prep have gone into making that talk. But I think we could turn on the lights now. I could do that from here because we can do that now. And we can have some questions. Please wait for Liz and the microphone before you speak. Thank you.
As usual, Con, it's difficult to answer a question after one of your talks because it's hard to argue with anything you put together.
But you'll try.
A very small question. What do we do with an overabundance of Subaru?
That's a question that's been on my mind too, Barry. It did occur to me that if you increase the suberin content of crop roots, are they going to tangle up with cultivation machinery? So you might need to modify your agronomics. I don't know the answer to it.
We have a difficulty with our waste as it is.
If it's staying in the ground, you know, as the roots of the plants and the bark of the plants, then is it waste? But yes, that's one of the questions that came to my mind because I've harrowed a few paddocks in the day, and I know how the roots can get tangled around it. So if they're not going away, is it just going to build up every year and become a problem? Don't know. There may be a way to build a chopping mechanism into it so that they break up into small pieces.
If I may, a comment rather than a question. Given our propensity for sex and given the fact that life fills every niche available, if we keep improving things with science, so we provide more of the wherewithal to support life, our numbers will go from 10 billion to 20 billion or whatever. It's happened after every change in technology. Where does it end? We're looking at this problem always from a human-centric point of view.
Absolutely. I don't have an answer to that, Barry. It's a really fundamental problem that humans face. We did it with vaccination and hygiene. Suddenly our population went up because people stopped dying. And then we did it with the Green Revolution. We provided a whole lot of food for people who otherwise would have starved, and our population went up. We do it every time we get an opportunity. We're going to have to learn some discipline along the way. I don't know how to do it.
Fail in our attempts to provide more and more.
Where's that microphone? Okay, it's here.
Just a quick one. We live in France for 4 or 5 months a year. And I can tell you every night there's something on the news about the environment, where there's bad things, where there's good things, lots of things. And then you get back to Australia and there is bugger all here. There's bugger information. The newspapers don't have anything. So how on earth do you get this message out, which is so important, when they don't care, our media don't care and don't believe we have a problem?
Well, our media is much more concerned with Barnaby Joyce's sex life than it is with the fate of the planet. Yeah. I mean, it's a serious problem.
Yeah.
Yeah. Microphone there. Yep. It's getting closer. Your turn.
Thanks, Sarah. Thanks very much for your talk. My name's Neville. What I've been wondering about, I don't know if you can answer, I think it's a complex question, global sea temperature. Now, we all know that once temperatures warm in the sea, because the water expands. And I understand where at 2 degrees for water, it's that stable mass, or let's say the smallest mass. And then when it freezes, it expands. When it gets warmer, it expands. But what research is being done on the overall the world's water with global temperature warming at special stages, because I know the ocean can be kilometres deep, and of course in coastal areas it's shallower, and that will expand more. And what interaction will the cold water have on the warm water, so that we can pinpoint with some accuracy, or within a certain area, what sea temperature rises will be. What the rise will be with the increase in temperature.
A couple of weeks ago we had Grant Hinner here from the Noosa Council, and he was talking about exactly that problem. Not in the specifics of the relationship between the expansion close to ice versus the expansion in the equator, which I think is what you're talking about. But it's really, really hard to predict sea level rises. What is believed to be the case is that sea level rise, at least in this century, is unlikely to be more than 600 millimetres. So the picture of the Statue of Liberty waving a chest high, that's just nonsense. I put that one in for fun. But certainly, again, it's that sensitivity. Is it going to be low sensitivity, or is it going to be a high level of sensitivity to temperature? Sea level rise, I would say within the next 10 years, we're going to get a much better picture of it. It's a bit like Shackham's picture of what goes on when the Ice Age ends, what's really happening. I think we're just starting to come to grips now with the science of sea level rise, how to measure it, how to predict it. Doesn't answer your question, but it's as good as I can do. So,
that talk was about as good as I've ever sat through. That was brilliant.
thank you very much.
So I've got a quick question. So what percentage of the CO2 in the atmosphere is attributable to coal?
Yeah, good question. I should have checked that, because I should have anticipated this one.
Because we talk about it.
Yeah, if you base the last data I saw on that was that electricity production is responsible for about 25% of greenhouse gas emissions, and coal is responsible for about 83 to 87% of that, depending on any one year. So 83 to 87% of 25% is down to coal.
So about 20%
Roughly.
of our problem is
Roughly.
coal-based.
Yeah.
Thank you.
That's why coal is the number one thing we need to focus on. Everything else, if you fix coal and replace it with an easily obtainable source of renewable energy, then you can start to do things with transport, you can start to do things with industry, you can start to do things with agriculture that you can't do at the moment because the electricity comes from coal. Once you replace that, then you're not just affecting electricity production, you're affecting a whole raft of CO2 producers that are responsible for about 60% of the total CO2 that we release. You fix that 60%, and then you only have to worry about agriculture and deforestation and one or two other minor things. So coal is the key. It's the trigger by which you shift everything. Okay.
That's a pretty amazing
sorry to be
point,
out of time.
really, to end on, because next week we've got the film about stopping Adani. And why do we want to stop Adani?
Coal is the key.
Hey, I think it's somewhere, I've read similar numbers, 20 to 25% of our problem will disappear if we get rid of coal. That seems such a simple thing to do, but beyond the realm of the possibility for certain people. But Rod, thanks again. Fabulous.
Thanks everybody for playing.
We've already given Rod books, Noosa and Kalula books, so we don't have a book for you today, I'm sorry, but I think what we'll do is buy you lunch. How's that?
Yep.
Okay.
That'll be an
All
honour.
right. Okay, so thank you very, very much, everybody. I think Rod deserves another round of applause.